Hello, everyone. So welcome to the first lab briefing of this course. In this video, I'm going to talk about some of the more fundamental concepts you need to know in order to complete lab one and go over the tasks briefly as well. Okay, so since this is the first lab, we're going to get introduced to uh, the two most fundamental physical quantities in electrical engineering, namely voltages and currents. And we're going to learn how to set up the circuit to measure voltages and currents in a circuit. Okay, so before we start talking about voltages and currents, just want to quickly talk about electrical engineering so to sort of give a motivation into voltages and currents, is that electrical engineering, if you think broadly about it, it has to do with either generation, storage, transport, and conversion of power, um, or it has something to do with information and its sensing, storage, processing, and transfer, right? So broadly speaking, these are the two branches in electrical engineering. You can have um, some things in between, or most of the time, both of these aspects of electrical engineering will have to come together in order to make a device. Um, but the idea I'm trying to go for here is um, power is basically energy, and information is also mostly stored in some sort of potential energy, either electric or magnetic, right? And then there's this notion of having to transport that energy or information from one point to another, right? So there's a notion of energy, and there's a notion of flow of that energy from one point to another whenever we're talking about power or information within electrical engineering, right? So there has to be something that carries this energy and flows from one point to another, and that something is charge, okay? And that charge can be electrons, holes, or ions of different kinds. But the charge is the fundamental quantity, and its units is coulombs. It's measured in coulombs. Okay. So this charge, it carries some electrical potential energy, and you can move that charge from one point to another, causing a flow of that energy or information from one point to another. Okay. So now if we now how does that relate to voltage and current, right? So basically, when we talk about voltage, we're referring to the energy, um, electrical potential energy of the unit charge. Okay. So if 1 coulomb of charge has 1 joule of energy, then we say that the potential is 1 volt of potential. Okay. And current, on the other hand, is the flow of charge per unit time. So through a point, if there is 5 coulombs of charge going through it in 1 second, then we say that the current is 1 amperes. Okay. So mathematically speaking, voltage is energy per charge, and that's volts, measured in volts. And current is charge per unit time, measured in amperes. Okay. Now, if you take the product of these two quantities, voltage times current, right, you get something that has the dimensions of energy per unit time, and we know that is power that we were talking about earlier, right? And it's measured in joules per second, or that's equivalent to 1 watt. Okay, so let's get a little better understanding of voltage. So when we're talking about voltage, we're mostly concerned with the change in voltage, right? Um, so we're converting energy from one form to other. So for example, if you have a battery, that battery is converting chemical energy into electrical energy. And so when an electron goes from one end of the battery to the other end of the battery, say from point A to point B, then then the chemical energy is converted into electrical potential energy, and that electron gains some potential, it gains some energy, right? On the opposite side, if the electron, say, goes through a coil, similar to one you may have in a heater, then that electron loses energy or potential, and that lost energy is converted to heat, right? So it's always we're always concerned with how much energy is changing, or that translates to how much voltage is changing from one point to the other, right? So that's why whenever we talk about voltage, we're always talking about potential difference. Mostly we're talking about potential difference between 2 points, point A and B. And that gives us a measure of how much energy, what potential difference there is in energy between the 2 points. Okay. So another way of looking at it is voltage is electrical potential energy per unit time, right? So if you've taken any classical mechanics courses, whenever we're talking about gravitational potential energy also, we don't have a, what do you call it, an absolute zero of gravitational potential energy, right? So for example, this mass, what potential energy does it have? It has a potential energy of mgh, but that is in reference to this ground, right? We say that the potential energy of a mass on the surface of the earth is zero, but that doesn't mean that it doesn't have any potential energy, right? So for example, if I dig a hole, then this mass can fall down and that potential energy is converted into kinetic energy. So it does have some potential energy even at the surface of the earth. But we've just arbitrarily chosen this point as a reference, as a zero potential energy reference, right? So anything below it would have negative potential energy. So that is just drawing the parallel between gravitational potential energy and electrical potential energy, similar to how we choose a reference of zero potential energy, right? We choose a 0 point in our circuits as a reference point to make any voltage measurements, okay? And so in mechanics, we normally use surface of the earth or ground as the reference point. And so the reference on an electrical circuit is also referred to as ground sometimes, okay? There might be some difference between a reference and a ground, depending on for larger circuits. So when we say ground, it technically means it's actually grounded to the earth, but a reference can be something other than that as well. Okay? But for a beginner's understanding, just understand that a reference ground is a point on the circuit where we say that the potential is zero or the voltage is zero, and then we can measure other node voltages with that reference. Okay. Okay. So next, all right. So let's see. So currents and voltages are fundamental quantities in electrical engineering. Okay, and they're so fundamental that any device is described in terms of currents and voltages, right? It's in fact called the IV relationship of a device, okay? And you can have any kind of relation between current and voltage, right? You can have, let's see, you can have exponential, you can have piecewise functions of current and voltage, you can have a simple linear function, right? So you can have all different kinds of relations between I and V, current and voltage, and the diversity of these relations gives us the diversity of devices that you can use to do different things and build useful devices, useful hardware, let's say. Okay, so as this is the first lab, we'll explore the simplest relation between current and voltage, right? And the simplest solution I can think of for anything is equality. Right? So I can say V equals I, but this doesn't really work, right? Because there are two different physical quantities. They can't be equal. So we'll insert um, a, a constant of proportionality, and that converts the units properly. Okay, so this is the simplest relation between voltage and current that we can think of, and that a device that has this relationship is called a resistor. Okay, and this relationship between voltage and current is what we call Ohm's law. Okay, and the unit of this constant of proportionality is well, this value is called resistance, and it's measured in a unit called ohm after the same guy. And its symbol is this Greek capital omega symbol. Okay, so the circuit schematic symbol for a resistor is like this. And so what this relation is saying is that the potential drop between the two across the resistor is directly proportional to the current flowing through it, and the constant of proportionality is the resistance value R. Okay, so that's Ohm's law for you. Okay, all right. So now we learned about voltage, we learned about current, and we learned about a simple device that that has the simplest relation between its voltage and current. Now let's learn about how to measure voltages and currents. Okay, voltage is measured using a device called a voltmeter. Its circuit symbol is this V, and notice it has two ends to it, right? And we said that voltage is always measured as a difference between 2 points, or the potential drop between 2 points, right? Potential difference between 2 points. And so if we want to measure the voltage across a resistor, then we have to connect the two leads of the voltmeter across the resistor like this, okay? And then now what you'll notice is this is what we call a parallel combination, right? By definition, parallel means that the voltage across two devices is the same. Okay? So if so right now the voltage across the voltmeter and the voltage across this resistor is the same, and so whatever the reading the voltmeter shows is the voltage across the resistor. Okay, so this is the symbol for ground in a circuit. This is what we call a power supply. It has a positive and a negative V. Okay, here I just want to sort of make a distinction between what a schematic symbol is and what a circuit model is. So a schematic symbol is just a symbol that you would use in the circuit to identify a device, right? So for example, voltmeter looks like this. This is the symbol for a resistor. But a circuit model is something different, right? So this voltmeter, it's a very complicated device. It has a lot of internal parts and whatnot, but we can sort of model it as simplified as a voltage measuring device and some non-ideal resistance that that it introduces into the circuit whenever we connect it, right? So right here, we're just showing an ideal voltmeter connected to across this resistor. But this voltmeter actually has some resistance of its own that we can model, okay? So a complicated circuit within the voltmeter, um, we can sort of simplify it into this model of an ideal voltmeter plus a parallel resistor. Right? So this is a circuit model, and you just have to make a distinction between schematic symbol and a circuit model. Okay, this will be important to keep in mind for your exam. Okay, now current is measured using a device called an ammeter. The schematic symbol for an ammeter is simply just an A with a circle. And now, if you notice, an ammeter also has two leads, right? But if you think about current, you're measuring, you're counting how much charge is flowing through a single point in the circuit, right? So for example, how much current is flowing through the resistor. So it's like you're sitting here and you're counting how much charge is flowing through. So now the question is, if that's the case, then how do you connect? Why are there two leads, right? So why don't I just poke right here and then count? That's not how it works, okay? And the, a lot of students, a lot of beginner students also try and connect an ammeter across the resistor like this, right? To measure the current through the resistor. And that's wrong. Why is that wrong? Because if you connect it this way, then there's going to be some current flowing through the resistor, and there's going to be some current flowing through the ammeter, right? These two currents are not the same. Right? They need not be the same. And so there's no way that the ammeter can measure the current through this resistor. Now, in order to measure the current through the resistor, you need to make the current flowing through the ammeter the same as the current flowing through this resistor. And the way to do that is you need to create a break here, right? You need to break the circuit and insert the ammeter where you created that break. So now the current flowing through the ammeter is the same as the current flowing through this resistor. And so whatever you measure for the ammeter is the current flowing through the resistor. Okay. Again, similar to the voltmeter, whenever you insert an ammeter, it introduces some non-ideal resistance into the circuit, and that we can model using a series circuit, a series resistor like this. Okay, so this is the circuit model for an ammeter. All right. Okay, so we've learned about voltage, current, Ohm's law, resistance, and how to measure currents and voltages. Now let's look at the lab and what you're going to do. Okay, so for the folks who have the 82 and everything, all of the kits that you need, um, you'll be doing this version of the lab. The first task is a hands-on task with the 82 and whatnot, and all of the kit. The second two tasks are all LTspice based. Okay. For those of you who do not have either the 82 or the kit or the DMM or neither of them, then you will just do the two LTspice tasks, right? Task 2 and task 3. So there's a different document, but it's just a document with the task 1 removed. All right. So what are you going to do in each of these tasks? Okay. So first task, task 1, what you're simply doing is you're generating some voltage with a DC supply source, right? And you're trying to generate different voltages, right? +3, -3, and in step 2, you're trying to supply 7 volts, right? 4.122 volts. You're just playing with the supply source, circuit symbol like that, and obtain different voltages, right? Part 4 and part 5, you're applying Ohm's law, basically. You're gonna apply certain voltage across a 330 ohm resistor, and then you're gonna measure the voltage and the current through it. Right? Oh, actually, no. You're just gonna draw a circuit to show how you would measure the current. So you're not actually doing any measurements of current at all. So you're calculating this using Ohm's law, and this is just drawing the circuit. That's pretty easy. Task 2 with the LTspice, we're doing a verification of Ohm's law. So we're building the circuit in LTspice with a power source, a resistor, and then we're going to apply different voltages. You're going to change this voltage from, um, let's see, from 0 volts to 0.5 volts with a reasonable step size, and make sure that step size is at least, at most 0.5 volts. Okay, so you can go 0, 0 0.2, 0 0.5, 0 0.81, right? And you're going to collect the current. You're going to run a DC operating point, what's called a DC operating point simulation, and read off the current going through the resistor. Right? So you're going to make a table of applied voltage and the currents, and you're going to jot down these values, right? So later when you're doing a write-up, you're going to plot these values on a graph with the voltage on the x-axis, current on the y-axis. Why are we doing that? Because voltage is your independent variable. That's the one you're controlling, and current is the one that's that you're measuring. Okay, so in general, you put your independent variable down below and the dependent variable up here. So you're gonna get a plot. It's a resistor, so I hope you get a straight line. And then from that, you're gonna estimate. Are you gonna estimate? Yes, a part A. You're gonna make an estimate for what the resistance is. And how do you estimate resistance from this plot? Right, so you're gonna look at the slope. And so what is the slope of this line? Right? So you have I as a function of B, so it has to be 1 over R. Right? So you can calculate what the slope of this line, and 1 over that will be your estimate for resistance. Okay. Right. So in task 3, we're gonna do the opposite exercise. Instead of changing the voltage, you're gonna change the resistance from 1 ohms to 10 kilo ohms, and just make sure your step size is reasonable. I say at least, at most, 1,000 ohms step size. Right? And then again, you're going to do the same thing. What you're going to do is you're going to measure the current for each resistance. Okay, so you're going to measure, get a resistance, measure the current, record the voltage and the current. So you're going to record both the voltage and current, and then what do you expect the relation between I and R to be, right? So give it a thought. What do you expect the relation between resistance and current to be? Okay. All right. So those are the 3 tasks. I just went over the task, but you don't know how to do that yet, or you don't know how to use the equipments yet. So for that, I'm going to take you over to the necessary resources. Okay. So let's go over to, where is my, okay. So here, you're going to find under lab manual experiment 1, there's a list of videos and documents that's going to help you understand the equipment and how to get started with them. Right? So first of all, you have the task list. And then next you have instructional video. So that one just goes and talks about voltage, currents, and Ohm's law like I just did. The second video talks about how to use the DMM, right? The handheld multimeter. The third video talks about analog discovery 2 and how to use it and how to set it up for as a voltage source, how to measure stuff with it. And lastly here, well, that's just the task list. What I wanted to show you was under resources. Yes. So under resources, there is an LTspice tutorial. So this will tell you how to how to get started with LTspice, and how to build circuits, how to run simulations. So it's introductory uh, video. Um, and for those using the 82 and building circuits or starting to build circuits, I will also point you to these two resources, the resistors and capacitor labeling guide. So for now, just focus on resistor labeling and then breadboard. Okay, so what is a breadboard? And so this is a breadboard, and this is where you will construct circuits with your resistors and everything. So you need to start learning how this works and how to build circuits on it, how to efficiently build circuits on it, right? So those are the resources you have. Just make use of them, and um, um, let me know if you have any questions. Okay. All right. So that concludes the this quick lab briefing for lab 1. It went a little bit longer because this is the first lab and there's a lot of new things that you're getting introduced to. But yeah, starting next lab, I'll try and schedule like a live lab session, which I'll also record that you can participate in if the time works out for you. And it will be slightly shorter than this, maybe 15 minutes to 20 minutes. I think today we're running into 25 to 30 minutes here. Right, but yeah, let me know if you have any questions. Office hours will be posted soon. I haven't received all of the surveys from all of the 75 students yet, but now I'm just going to close out the survey and take a look at whatever I have so far. Okay, so thank you everyone for listening to me, and good luck.